So in the previous lesson, we looked at the work that would be done on a test charge Q if we were to move it from some point A to some point B, and we had some force which was acting on it by a collection of point charges. Well, what we worked out is if we wanted to move the charge from far away, let's say infinity, in up close, is that the work done on that charge will be equal to Q times the potential of the system. So that would be the potential due to those point charges. Now, let's look at how much work would be done in order to put together a point charge distribution. So first of all, let's say we take in some charge Q1 from far away, and we're going to put it at some position which is given by R1. Okay, now remember that position is from the origin to that point charge, and that point charge is Q1. Now, how much work would be done on bringing this point charge in from far away and putting it into the space? Well, quite clearly that the potential there is going to be zero. We've got no other point charges there. So the work that would be done on our first test point charge is going to be equal to zero. Now let's bring in another point charge, which is going to be Q2. And it's going to be at some position given by R2. So how much work will be done on the point charge Q2? Well, that is going to depend on the potential of the point charge Q1. And we can write the work that will be done on 2 as the charge 2 multiplied by the potential of Q1, which is given by 1 over 4 pi epsilon naught by Q1 by Q1 over the distance between the two charges, which here we're going to call it the distance of 1 to 2 minus R prime, which again relates to the source 1, 2. Okay, so that's the work that will be done on our point charge number 2. Again, this distance between here and here, between the two charges, is given by R12 minus R prime 1, 2. Now let's take in another point charge. We've got some other point charge, which is going to be Q3. We're going to put it at some position given by R3. Now how much work will be done on Q3 in bringing it from far away and up close to where Q1 and Q2 are? Well, what we're going to have now is a contribution from both the potential due to Q1 and the potential due to Q2. So therefore the work on point charge number 3 will be equal to Q3 multiplied by 1 over 4 pi epsilon naught Q1 all over the distance between Q1 and Q3 plus the potential due to Q2, be 1 over 4 pi epsilon naught Q2 all over the distance between charge 2 and charge 3. And now clearly if we were to bring in another point charge Q4, the work that will be done in Q4 will depend on the potential of Q1, Q2 and Q3. Okay, so just this here distance is given by R1, R23 minus and then we've got this other distance, which would be R13 minus R prime 1, 3. So let's write this out a little bit neater now. Let's say we've got like a collection of point charges, and we're going to do it now for any number of point charges. So the total work that will be done will be given by 1 over 4 pi epsilon naught. We've got a double sum for our point charge, so we go I is equal to 1 from 1 point charge up to n, from j is equal to 1, and this is for j is greater than 1, so that we don't count each point charge pair twice, by qi by qj divided by the distance between them. So it'll be r ij minus r prime ij. So we can write this out a little bit neater. We can just write it out in terms of the potential. And what this will give is the work will be equal to 1 over 2. Now what I've done here is I've divided this by 2 so that we don't count the point charge pairing twice. Okay? Which would be the sum I is equal to 1 up to n by qi by the potential of I. Okay, so this is the work that will be done to assemble some distribution of point charges, but of course it's also the work that will be done in order to dismantle that collection of point charges.